Welcome to the Explainer. So if you've ever tried to use an AI to generate a really complex software architecture diagram, you've probably experienced a very specific flavor of frustration. You give the AI a perfect prompt. It spits out the code. You go to render it, and it just looks like a massive plate of spaghetti. You've got arrows crossing everywhere, text boxes overlapping, just total visual chaos. Well, today, we're going to actually solve that frustrating mystery. We're unpacking Osamu Okumura's brilliant research on the Skills Filter Framework Volume 3 to figure out exactly why AI diagrams turn into such a tangled mess, and more importantly, how we can cure it for good.
Okay, let's dive right into this. Here is our map for today. We'll start with the diagram collapse mystery, look at a language-independent pathology, introduce the pre-rendering layout guard, break down the control equation, explore 4 major breakthroughs, and wrap up with the AI collaboration shift.
All right, Section 1, the diagram collapse mystery.
Now, you might be wondering about this. AI models like Claude or ChatGPT, they are honestly remarkably good at generating code, parsing logic, and understanding whole systems. Yet, when we ask them to output code for complex C4 architecture diagrams, specifically container and component diagrams, they fail spectacularly. So why do these AI-generated architecture diagrams always seem to collapse? Why do all the boxes overlap and the arrows just crisscross into oblivion? Well, Okumura's research identifies this specific issue as a Type L layout collapse. And to fix it, we basically have to treat this not as some random glitch, but as a structural mystery that we need to solve together.
The absolute master key to unlocking this whole problem is understanding a concept called DAG, which stands for Directed Acyclic Graph. In a DAG, arrows flow in a specific direction, and there are absolutely no closed loops or cycles. Basically, you can never follow the arrows and end up right back where you started. This is crucial because standard rendering engines, which power tools like PlantUML, rely on the Sugiyama algorithm. And the very first step of that algorithm, assigning layers to the graph, absolutely requires a DAG to function. If there's a loop, the engine literally panics, the layer assignment fails, and boom, you get a layout collapse.
And this completely nails exactly what's going wrong. Think about a standard sequence diagram. It works perfectly top to bottom. The flow of time automatically guarantees that it's DAG compliant, because, there are no loops in time. But then look at C4 diagrams. They heavily feature bidirectional dependencies. Service A calls Service B, and Service B calls Service A. The moment the AI faithfully codes that bidirectional arrow, it creates a closed loop. That loop instantly shatters the DAG rule. The rendering engine's first step fails, and visual collapse occurs. It's not a bug, it's a fundamental structural incompatibility.
Moving on to Section 2, a language-independent pathology.
Now, what's really interesting about this slide is that for a long time, researchers actually wondered if this collapse was simply an issue with non-English characters. Like, was it just a font issue? To test this, Osamu Okumura ran a fascinating, highly creative experiment generating complex diagrams based on 30 Japanese haikus and 30 English Shakespearean sonnets. And look at that pre-filter failure rate. English sonnets had a 58% layout collapse rate, and Japanese haikus had a 60% collapse rate. That is practically statistically identical. This proved once and for all that Type L collapse is a universal, language-independent pathology. It is fundamentally about the structure of the graph, not the font or language. And notice what happens when Okumura's filter is applied. The success rate rockets to over 95% for both languages.
All right, Section 3, Pre-Rendering Layout Guard.
So how exactly did they achieve that massive jump to a 95% success rate? Well, enter the hero of our story, the pre-rendering layout guard. Think of it as an interceptor. It basically acts as a protective shield sitting right between the AI, the LLM that's generating the raw code, and the PlantUML rendering engine. The core philosophy here is super simple. Never blindly trust the AI's raw output. The AI is definitely going to output loops because it's trying to be logically accurate to the system, but the engine is going to choke on them. This guard intercepts that raw code before it ever reaches the renderer.
This represents a massive shift left in how we handle AI output. Instead of waiting for the engine to draw a completely messy diagram and then, trying to fix the code after the fact, we fix the data before the engine even sees it. The interceptor works in 3 steps. First, it parses the structure. Second, it performs a topology judgment, which is basically checking for those dangerous loop-creating bidirectional arrows. Finally, it auto-corrects them, forcing the graph into a DAG-compliant structure. It's a preventative cure rather than a messy post-rendering bandage.
Which brings us to Section 4, the control equation.
Okay, but how does the system actually know exactly what to autocorrect?
This is where we shift into the mathematical backbone of the solution, elevating this from simple bug fixing to pure computer science. Take a look at this control equation. E equals alpha C plus beta W plus gamma D. This equation is actively running in that middle topology judgment step we just talked about. It mathematically predicts E, the total layout collapse energy, right before step 1 of the Sugiyama algorithm attempts to assign graph layers. It calculates the risk based on the number of nodes, the weight of the elements, and the complexity of the dependencies. If the collapse energy E gets too high, the system knows it absolutely must intervene.
What is literally mind-blowing to me about this equation is that Okumura realized it actually mirrors the exact math used in physical structural engineering. The same topology optimization principles used to ensure a massive steel bridge doesn't just collapse under its own weight are being applied right here to ensure an AI-generated diagram doesn't collapse under the weight of its own complex dependencies. It's literally bridging software architecture with physical architecture.
Let's move to Section 5, 4 major breakthroughs. So the crucial point is that with this mathematical foundation in place, Okumura's Volume 3 research achieves some truly remarkable things. This framework moves far beyond just technical bug fixes. It establishes a super robust methodology for how AI-generated visuals should be handled globally, and outlines 4 major breakthroughs that chart a very clear course for the future of AI tooling.
Let's rapid fire through these 4 real quick. Breakthrough 1 is Rule 12, which is a metacognitive rule we'll discuss in just a second. Breakthrough 2 is the simplification of complex terminology to make this whole system ready for global business standards. Breakthrough 3 is layout curing, specifically completely separating explanation text panels from the charts themselves so they never overlap, ensuring total visual clarity. And Breakthrough 4 is the Sonnet 18 roadmap, which lays out a 4-star priority plan for proposing this entire framework as an open global standard to massive organizations like ISO and W3C.
Finally, Section 6, the AI collaboration shift.
Let's move to and see how this builds into our final and perhaps most philosophical takeaway about how humans and AI should actually interact. It all comes down to Rule 12, 1 diagram, 1 explanation. When we work with AI, it constantly tries to overcouple information. It wants to mash every piece of data, every dependency, and every explanation into a single, dense output in the name of efficiency. Well, Rule 12 dictates that we must never blindly accept this. Overcoupling creates massive cognitive overload for humans and layout collapse for rendering engines. We have to separate, structure, and validate the information independently. I want to leave you with this incredible quote directly from the research. The pre-rendering layout guard provides a pre-designed discipline to the unruly swarm of AI outputs. AI is brilliant for sure, but it is an unruly swarm. It absolutely requires our structural discipline. So as you go back to your desk today, ask yourself, where else are you accepting the unruly swarm of AI output without a shift-left mentality? How can you apply strict pre-designed validation to your own daily collaborations with AI to stop your projects from visually or logically collapsing? Think about that. Thank you so much for joining me on this explainer, and keep learning.